Hello everyone, this is chapter 5 for AE357 Petroleum Technology. In this chapter 5, I will talk about the catalytic reforming and isomerization. From the previous chapter, we do understand what the CDU is about and the specific products coming out from the column. In this chapter, we will focus on the upgrading some particular products. In general, two techniques that we will talk is reforming and isomerization. Well, let me remind you about CDU, the crude distillation unit that we talked about in the previous chapter. The product from this unit including of gas, naphtha, kerosene, diesel, and so on, the gas oil. In this case, we can make the crude distribution curve. The one that we will focus three of these. The first one is off gas, and then straight run gasoline, and the third one is naphtha. So in this case, we have learned how to get the number of the percentage of those products. For example, off gas in this case can receive about 2%, while the straight run gasoline we will get about 7% of straight run gasoline and also 14% for the naphtha. When we talk about off gas can be used can be used as the energy source for heating the unit, while the gasoline or straight run gasoline can directly used in the gasoline pool, while the naphtha, which contain some complex hydrocarbons that processes carbon atom between 5 to 12. So with a variety of hydrocarbon mixture, the quality is not very good in terms of octane number. So it is better to improve the quality of octane number first for case of naphtha. Let me give you an idea what the octane number is. The octane number is the measure of its anti-NOx properties, which is equal to the volume percentage of isooctane to the mixture of N-heptane and isooctane. The octane number can be classified into two categories here. The general octane number is an average of these both values. For the research octane number is the value obtained from a test engine run at the speed of 600 rpm, while the model octane number is a value obtained from the test engine at a higher speed at about 900 rpm. According to that, when we specific on different chemicals, this table lists octane number regarding to the number of the carbon content of C4 and C6. You can see that in this case we're choosing C4, normal butane and isobutane. According to this, we can roughly say that isoparaffin has higher octane number compared to normal paraffin. How about C6? we select the chemical of we use hexane as an example. We take normal paraffin, normal olefin, naphthalene, and aromatics, and what we can see here is that the octane number of aromatics is a bit higher than these two olefin and naphthenes, and down to paraffin here. According to the octane number regarding to C6 in different chemical structure, we can rank that the octane number of aromatics is higher than olefin and naphthenes and higher than normal paraffin. Well, these are the examples of C4 and C6. Now we list the octane number of C3 to C8 in different chemical structure, which including normal paraffin, isoparaffin, naphthenes, and aromatics. This figure, after plotting all the octane number for each one, this figure will each you for the memory of octane leading consequence. Oops. Yeah. Okay. Now let's go to the first reaction of the octane quality improvement, which is according to this is catalytic reforming. Before talk about the reaction, let's understand a bit on the naphtha term. Naphtha is defined as the petroleum with the boiling point between 30 degrees Celsius up to 200 degrees Celsius. So in this case, a mixture of C5 to C12 can be contained in the mixture. The naphtha can be classified into light and heavy one. So for the light naphtha, we include the carbon content of C5 to C6 in carbon atom, and for about heavy naphtha, it will be a mixture of C6 to C12 carbon atoms. So with the higher molecular weight of this hydrocarbon, the boiling range should be higher in the higher range as well. So for the light naphtha, we can assume that this can be direct use as the straight run gasoline. However, the heavy naphtha should be carried out in the catalytic reforming to improve the octane number. So in this case, the feed of the reaction is heavy naphtha. So with the mixture of paraffin, naphthenes, and aromatic in this particular volume percent, the octane number, the result octane number is not high in this case, which is about 20 to 50. So so when we feed this heavy naphtha to the reactor with it's operated at 500 degrees Celsius and medium pressure over the platinum based catalyst, what we will get in the products is something, some mixture that can increase the octane number up to 30 to 100, and of course we can get undesirable products of coke as well. Those examples are about reforming by dehydrogenation or cyclization. However, we have another two reactions that can improve the quality of the octane number. One is isomerization and the other one is hydrocracking process. Now let's take a look on the isomerization first. The isomerization is the reaction that will reconstruct the normal paraffin to isoparaffin or the blanch one. This will be talked about later. Another reaction is hydrocracking. In this hydrocracking we do have to add hydrogen into the thick hydrocarbon. The example here is decane, which has the octane number is quite low in negative value, but after the cracking process, so what we get is light hydrocarbon together with some smaller comparing to the feed. The octane number increased to 75. However, another hydrocracking process of aromatics here also involved to reduce the chemical, some hazardous chemical, but not reduce much in terms of octane number. So in this case, we may have to reform this for C7 and put some hydrogen into this. So then what we get is aromatic 1 or benzene ring that can be used after cracking. We can use that in the gasoline pool. We give you the idea of the process here. The naphtha which is out from the CDU will be treated to eliminate sulfur by the hydrotreating unit, and then the product is the products of free sulfur will be separated in two things, light naphtha and heavy naphtha, based on the different carbon atom. The light one will be processed in isomerization unit, while the heavy one will be processed in reformer unit. The product from isomerization unit will be called as isomer, while the product out of the reformer unit will be called as reformate. To make you understand about the reformer, we will talk about the involved reactions. As you can see here, the first one is the reaction of dehydrogenation of naphthalene. In this case, in these two examples, methyl or cyclohexane containing an octane number of 94 can be increased to 110 of octane number by taking out hydrogen in the dehydrogenation process. In this case, the octane can be increased from 80 to 110 as well, from the dehydrogenation of dimethyl or cyclopentane. In this particular one good product, but one good byproduct is hydrogen. you have to think about where will the hydrogen be used to, be used for. Okay. This is the dehydrogenation of paraffin. So in this case, the reaction is extremely important since it can boost the octane number from nothing to 84. This reaction is the combination of the dehydrogenation, take the hydrogen out, and also make the cyclization from the straight chain to the aromatic one. One of them, the last that we will talk about is isomerization. The isomerization can change general normal paraffin to isoparaffin. This reaction can as well take place for the reforming because it can boost the octane number from -30 to 75. However, it involves some cracking reaction. The cracking reaction here is we cannot change much of the octane number. However, think about why the reaction of toluene have to, why does toluene has to be cracked out to just to become to benzene. This reaction refers to the cracking of toluene to benzene. It will a bit low. It will lower the octane number from 110 to 14. However, this reaction is quite important. You may wonder why do we have to let this reaction go through. This reaction is the cracking process of toluene to benzene. However, the octane number of this feedstock will be lower from 110 to 14. Students have to think about what is the reason that we still let this reaction take place in the process. Now, let I put them together. The involved reaction in now I can put all the involved reaction together here in one diagram. You can see from these there are four main reactions. For example, hydrocracking, dehydrocyclization, isomerization, and dehydrogenation. Here, each reaction is taking place over catalyst, either M or A. M stands for methyl catalyst, A stands for acid catalyst. Of course, when the cracking is involved, some of oligomerization can take place as well. So the more oligomerization, the more undesirable product will be formed. And what I am talking is the coking process. This will produce coke, which can deposit on the catalyst surface. So when the active side of the catalyst decreases, it will lower the reaction extension. ในที่นี้จะเป็นการขยายความนะครับของการเกิดโคกกิ้งในส่วนที่เราพูดถึง สำหรับปฏิกิริยา reforming reaction ใช่ไหมครับซึ่งเมื่อกี้ได้กล่าวไปแล้วว่าโอกาสของการที่มันจะมีcrack product เกิดขึ้นเนี่ยก็อาจจะทำให้เกิดoxymerization เกิดขึ้นได้การที่เกิด oxymerization เกิดขึ้นได้ก็อาจจะมีการไล่ไฮโดรเจนออกไปเมื่อไล่ไฮโดรเจนออกไปเนี่ยก็ทำให้คาร์บอนไฮโดรเจนเรโชเนี่ยมีลักษณะที่น้อยลงไปเรื่อยๆนะครับทำให้คาร์บอนเนี่ยมีการสะสมตัวแล้วก็อาจจะขยายตัวมาปิดกั้นตัว active site นะครับของตัว catalyst ซึ่งการขยายตัวมาปิดกั้นตัว active site ของตัว catalyst ก็เลยจะทำให้catalyst นั้นมีสภาพที่ลดความสามารถลงไปหรือที่เราเรียกว่า deactivation ของ catalyst อันนี้คือหนึ่งในการลดความสามารถของ catalyst นะครับซึ่งเราได้เคยกล่าวไปแล้วล่ะโดยทั้งหมดนี้จะมีทั้งหมด4วิธีนอกจาก coking ที่เกิดขึ้นก็จะมี poisoning ใช่ไหมครับแล้วก็มีsintering หรืออาจจะเป็นphase transform นะครับจากการ sintering นั่นเอง This is an example of the dehydrogenation of cyclohexane to produce benzene. Of course, this can increase the octane number of the chemical. Since the reaction is take place at 500 degrees Celsius and medium pressure condition, we have to find out for the Gibbs energy, and it is about 20.6 kilocalorie per mole. This example asks you to find out how much benzene can produce in case of input of 1 barrel of the cyclohexane and some pressure built up by the hydrogen regarding to the ratio of the 10,000 cubic feet per 1 barrel of the cyclohexane. In this table, it summarizes how the behavior of the reactions involved in the reformer are. There are three groups of the reactions taking place in the reformer, starting with dehydrogenation, and then isomerization and hydrocracking. For the dehydrogenation, the reaction is quite rapid. For the isomerization and hydrocracking, the reaction starting to be slow. And of course, in this case, the reaction for the rapid reaction will take place in the first reaction, and then for the one that have slow reaction will take place in the last reaction. The example of the dehydrogenation is naphthalene dehydrogenation and naphthalene dehydroisomerization. The reaction is quite fast, following with the paraffin isomerization. And furthermore, for the hydrocracking, the reaction is quite slow. When we look at this column, we can see that the first reactor or the first reaction, which is dehydrogenation, it can produce hydrogen, which can be used later in the last reactor here for the hydrocracking process. And then when we look at this column, the reaction is some endothermics and exothermics. So what does it mean? It means we need some heater and cooler in the system. What I mean is heat exchanger in the system before feed the raw material into the reactor or cool some feed raw material to the reactor. However, all of these can produce good octane number. Better octane number. This slide, next slide, showing how they put the heater in the configuration in the system. So we do have to put the heater for the first reactor and then some heater again to push the reaction forward. This is one kind of configuration. We do have the second configuration here by heat up before the reactor, heat up before the reactor, and heat up before the reactor. They also tell us about the temperature profile for each reactor as well as the product distribution. In this case, they put the reactor together in one column. However, the heat exchanger trains are configured in this type. So the first one requires some big heat exchanger to increase the reactor, increase the temperature of the reaction higher than the lower reactor here. Now let's see if I would like to do the approximate calculation. The following empirical equation here provide approximate calculation for the reforming unit. As we know that the feed material of the reformer is heavy naphtha, so probably we have to know the basic information of the feed. For example, how much the naphthenes and aromatic containing in the feed. So when we know that amount, we can calculate what the C5 plus can be formed in this unit, and this C5 plus can be used to calculate how much C1, C2, C3 and C4 left from the reaction, and also how much the hydrogen can be produced. In this slide, in case that we know the exact chemical feeding to the reforming unit, we can use this conversion values to calculate the products that remain in the product stream. Okay, that's all about the reforming reaction. Now, from this slide, we will talk about the isomerization. The reaction is to reconstruct the chemical of the paraffin from the normal state chain to the branched one. So of course, octane number can be boosted up. However, isomerization is a bit different from the reforming. Isomerization is a reversible process that have a little bit in terms of exothermics. So the conversion of this will be lower when the temperature increase. However, the conversion is not totally complete like reforming, and this because of the reaction is equilibrium limited. And now we talk about of course the reforming and isomerization process require catalysts. In general, bifunctional catalyst is preferable. This is why we have to that's why we have the alumina for the Lewis acids, the Lewis acid size, and having the platinum or palladium deposit a little bit on the alumina matrix to involve the hydrogen in the reaction, which to prevent the coke deposit on the surface on the active side of the catalyst. In general, isomerization requires acid catalyst. However, when you have an acid catalyst involved to the reaction, the coking may take place. So what they usually do is to have the acid catalyst for the support, and then we do have the noble metal to prevent the coking. So in this case, we call this kind of catalyst as a bifunctional catalyst. So we have to we do have the alumina, which represent as acidic function of the catalyst. However, we also disperse the platinum or palladium in very small amount on the matrix of the alumina, and this platinum will when it is present of hydrogen, it can prevent the coke deposit on the active side of the catalyst. However, at this moment, commercial catalyst of zeolite is also preferred because the catalyst can handle the reaction at higher temperature, but in terms of product qualities, they are not significantly different. So briefly, in this chapter, we know what kind of reaction that can use to boost up the octane number, and also how configuration and thermodynamics behavior that can improve the way of putting configuration together. And I would like to ask student to find out more, read in the detail for the rest of the chapter. Thank you for watching, and goodbye. For the commercial one, we do also load noble metal or platinum and palladium on the zeolite. So in this case, we can boost up the reaction a bit higher than using on aluminum base. However, the conversion is not quite different. And the last one, this table will show the approximate guidelines of the material balance in isomerization unit. So in this case, if we have some C1, C3 up to C5, they will convert to the isoparaffin, which is high amount. In brief, octane number of the product is an important, and these two reactions can provide such a good quality. Thank you for watching, and see you in next chapter. Goodbye.